Okay, so today is the intro lecture where we will be, today's the first lecture, first session on genome sequencing and automata theory. So today we will be starting our discussion with the problem of genome sequencing. From a math point of view. So as far as mathematicians are concerned, genome sequencing seems like you just have, why is it not writing? Yeah. Genome sequencing seems like you just have the following characters A, T, C, G, and you have some random sequence that you are asked to predict. So from this point of view, right. So from this point of view, the one way you can translate this problem into a different problem is, say you have some irrational number, like say let's take a classic one, pi, right? 159.216 and so on. So beyond that, we want a way to, similarly, we're also interested in predicting the next digit of pi, right? So if you look at it, these two questions are asking pretty much the exact same thing. Over here, in the case of pi, instead of having just ATCG, I just have the following, like 1, 2, 3, all the way to 9. So in both of these cases, I'm given a set of letters. And in this case, I'm also given sort of a set of letters. In this case, we call it the base 10 digits. And this doesn't really have a significant name. This is just a set of letters for our purposes. Also known as an alphabet, as far as automata theory is concerned. Anyways, so this sort of interplay, we want to use tools that we've used to sort of predict letters or study the digits of pi and other irrational numbers, and we want to use those tools to see if we can say anything interesting about genome sequencing. So that is just the necessary background. Everyone clear so far? I don't think I've explained anything much, but do we all going on? Awesome. Okay. Just give me 1 sec. Okay. If only I can erase this thing without issue. Oh, I can. Let's go. Typically just crazy. Okay. Okay, good. So now we are going to talk about our approaches in this project to trying to predict our genome sequence. And this is where automata theory makes its entry. Okay, so let's see. Okay. What we're basically defining is we're going to use the same approach of trying to go from instead of starting directly from base 10. Let's see, how do I explain this? So initially, while studying digits of pi, before we started looking directly at base 10, we started studying smaller bases. So we started studying base 2, base 3, base 4. An interesting yet boring fact about the digits of pi is that no matter which base you take it in, the distribution of all your n digits takes 0, 1, 2, all the way up to n. This entire distribution, as you go in number of digits of pi, you just get a uniform distribution. So this is somewhat of a boring find, and this is hopefully the find that we don't get in our study of genome sequences. Okay, cool. So, given that, I'm going to start explaining what we're doing basically from our base 2 to base n approach. So, we're going to treat our genome sequence, the alphabet of our genome sequence, as though it is just a base 4. Ah yeah, this is what I mean by not being able to erase most of the time. Right, okay. Okay, cool. So, in our approach, basically we're treating A, C, T, G is equivalent to our set 0, 1, 2, 3, which is exactly the same as our base 4 representation of a number. So, what do we mean by base 4? You guys understand base 4, right? Like, you understand the concept. Basically, like if I have a number 90, this is in base 10. If I convert it into binary, I'm going to get some huge string, maybe not so big string of numbers, that's in base 2. And similarly, I can convert it into its counterpart in base 4. You understand that, right? Do we all get the idea? Cool. Yeah. So that's all. That's basically just this correspondence. With this small assumption, we can go ahead with pretending that instead of actually predicting a genome, that we're actually instead predicting a number in some sense. Okay. So in comes our own cooked up concept called a third automata. So let me just bring my book. Okay, cool. So where's the thing? Right. Okay. So in the third automata, what is that? Will it go away? No, it won't. It went. Okay, that's great. That went as well. Okay. Oh, this thing freaks out. Automata. Okay. So first of all, what is an automata? An automata, you can think of it basically as a state diagram where I have state 0, state 1, state 2, state 3, state 4. Let's just take 5 total states for now. So an automata tells me how to move, is going to allow me to read a string of numbers. Say I have 0, 1, 0, 0, 0, 0, 0. And I've defined my automata with relations like, okay, I'm going to put 0 over here. I'm going to define these relations, okay? I am arbitrarily giving these relations between an automata, okay? And I'm going to define a starting state And basically this is something called a state diagram. And what I'm going to do is I'm going to feed this, or the automata is going to read these integers one by one, and it's going to traverse around the graph. And an automata is basically a machine that reads a word and accepts it or rejects it. And now, from this definition, now you should notice that you don't know what it means to read a word, you don't know what it means for us to have a word, you don't know what it means for to accept a word or reject a word. Yes? All you see right now is that I have given you some random diagram with some nodes, and I'm calling them states for whatever reason, and I'm inputting all these bits one at a time. So for now, for our intuition's sake, let's just take these inputs one at a time. So first one is 0, it'll go up. Okay, how about if you could unmute and just direct me to where each of these inputs is going to take my state. So you guys can go ahead and unmute. Okay, go ahead. So I'm starting at state 0, which is at the center over here. I read 0. Where do I go first? Hello?
To S1 state.
Yeah, that's right. So S1. Let me just use purple. Yeah. If this thing will select it. Great, okay, yeah. So I started at S. It did not select it, okay. Oh. Okay. Okay, I started at S1, S0, and I go to S1 because I've read a 0. Now next I'm going to read a 1. Where do I go next? There are two choices, so I make an arbitrary choice. Oh wow, this is not a good example at all, is it? Oh, I'm going to start from the beginning. I'm going to just take a better example, and I'm going to start from the beginning. I've accidentally taken a non-deterministic one. So
it is a unidirection. You take a S0, you go to S1 and S4.
No, it won't go to. Yeah, that's what I meant by a bad example. This one is called a non-deterministic.
Take another example and explain what I want to understand that one again.
Okay, so essentially, when you have an arrow leading. Okay, so given the same character, if you have two arrows leading to two different places, you sort of make a guess, and that's what that adds to the non-determinism of your automata. What I mean by non-determinism in an automata is that if I give the exact same input, I may not get the exact same output. So in this case, since there are two different arrows going out, right? The fact that I have two different arrows with the exact same character leading out to two different places means that if I put the same character twice, I have the possibility of going to two different places, right? And so by the definition I just told you about non-determinism, when I put in the same input again, I'm going to a different state. And so my automata is non-deterministic. So that...
There is no direction in...
I'm sorry?
There in automaton, there is no direction.
There is direction. There is a direction. I've drawn, right? In non-deterministic and deterministic ones, you have direction. Okay, so I said an automata is, let me write in bold the words that I haven't defined yet. A machine that accepts words or rejects it. Now first let's start by defining what a word is. So you and me have defined what an alphabet is, right? What is an alphabet? It is, for the example, it is our ATCG. For definition's case, you can say it is our finite set of characters or letters. Yes? All good? Cool. Okay. So, given our alphabet, we construct, our alphabet is typically denoted as sigma. Then we define a sigma star as the possible, all finite sequences formed by L as a letter or letters belonging to sigma. Okay. Now let's just construct what sigma star looks like. So sigma star is going to look like, why did I use that bracket? This one, yeah. Okay. Is going to look like, first I have the choice of, let me just take ATCG as an example, or let me take a simple example. I'll just take A comma B for now. Okay. So the first word, in some sense, this sigma star is the collection of all finite sequences, or it is the collection of all possible words formed by sigma. So let's actually write down some terms that belong to the sigma star. So in sigma star, the first word you'll have is the empty word, but you can't just put it as a space, so we denote it as epsilon. Okay. Universally, everywhere you're going to put epsilon as the as your empty word. Next you have A, then you have B, then you have AB, then you have BA, ABA, AA, anything. Okay, all possibilities are, all combinations are here. Okay, within sigma star. Now, what we're going to define is something called a language. So a language L is simply a subset of sigma star. So let's think about it in normal English words, okay? English words are just constructed from a sigma, which is just A, B, C, all the way down to Z. And so you have sigma cells that contains words like and, hello, but it also contains complete gibberish like ZXY. And so your English language is a subset of sigma star. Does this example at least give the intuition to everyone now? Excuse me for 1 second. Cool, I'm back. All right. Okay, so we understand the notion of a language, and by extension we understand what a word is, right? So a word is clear. It is basically some finite sequence formed by letters in sigma that belong to our language L. Okay. Now, what an automata does, or let me draw it actually better. Is basically you're going to have a language and you're going to input a word, and what it's going to do is it's going to either say accept or it's going to say reject. Okay, makes sense? Similarly, if I have another word and I have designed my automata to detect this language L, and I have a word that comes from some random sigma star that does not come, okay wait, let me just put this, does not come from L, then what is it going to do? It's going to reject my word. And that's the basic idea of what I want my automata to do. So an automata is used to recognize language or a given language. Okay. Now let's see. So what I'm going to define now is a deterministic finite automata. A deterministic finite automata is basically the following. So I'm going to have a set of states. I'm going to have a starting state S0. I am going to have, what else? Accepting states. I'm going to have my transitions. What's the last one? Is that 4 or 5? Yeah, 5 is for, no. Oh, right. How could I forget? Sigma. Yeah, there we go. Okay, so this behemoth of 5 things comprises what I call my automata, my DFA, my deterministic finite automata. So, a deterministic finite automata, in this, let's break this down, okay? So first I'm going to just list all of them by name, and then I'm going to draw an automata and explain what it means, okay? Set of states, starting state, F is my accepting final state, and yeah, this delta is my transition, and what do I mean by a transition function? It is basically a function that takes my current state. Okay, wait. Delta is a map from my current state, the ordered pair of my current state, and a letter from the alphabet, and takes me to a different state. Yes. Okay. And finally, sigma is my alphabet. And now it's time for me to actually show an example where this would make sense and doesn't sound like just a boring set of Greek letters. That is if my computer actually decides to scroll. There you go. Okay. So let's take a simple automata. I am going to take sigma is equal to a comma b. And let's see. Okay. So I want to, okay, let me just go ahead and draw it. S0, S1, S2. This is A. This is A. This is B. And this is B. This extra circle here denotes that this is the starting state. Now, for this particular example, I'm going to say that F, or my final state, or my accept state, is going to be the initial state as well. And so with this example, I would like to ask a question that won't be obvious now, but we'll break it down together, okay? What is this automata even doing? Yeah, go ahead.
My doubt is that in DFA, each and every state should have both the alphabet, no?
Yes, not exactly.
Okay.
So
there is no compulsion of having
yeah.
both the alphabets.
And what I'm going to show now is basically how words are accepted or rejected. So when I ask what this automata is doing, there are two things. Is what is it accepting? Accepts what? Rejects what? And so now we all have the intuition of what a word is, right? So it's just A, B, A, all sorts of random strings like that. Right. And now from this whole list of strings, there are two things. If I start over here, let me see if I can use a different color. God help this laptop. I'm going to murder OneNote someday. Okay, right. Oh great, I didn't even change it. There we go. Okay. So, the only criteria for a word like this to get accepted is for it to come back to its original state. Yeah? However, if my word, gets stuck somewhere, then it is a form of rejection. So, now I'm going to answer these questions myself about what kind of words this thing accepts. So, here we see that we're starting over here. Okay, we're going to input one, character. We get A, it goes to S1. We're going to input our second character B, it goes back to S0. It is accepted and it's okay. Similarly, I'm going to start with A, and then I'm going to take a B, and we're accepted again. Okay? I do the exact same thing here, A, B. Make sense so far? And so I've shown that these three words at least are all accepted. Now I'd like to ask AAB. Is it accepted or rejected?
It's rejected.
That's right. Because the second it goes over here and then goes over here, there's no way for it to go back over here, and hence your word AAB is rejected. Okay?
Okay. In case S2 is a dead state here.
So if you're asking if S2 is the accept state.
Yeah, dead state.
Yeah, then that was going to be my next example. So that's a good question. Let me erase everything with some great effort. Okay, I'll just rewrite whatever. All right. Okay. So now if S2 was my accept state instead, let's reevaluate these words. Okay. So let's take the first example. Oh, for the love of God. Yeah, there we go. Great. Okay. So we start in S0 with an A. We go to S1 with a B. We go back to S1, S0. With an A, we go back to S1. With another A, we go to S1. Our word is accepted again. Similarly, let's take A, B, B. So first we go S0, S0 to S1 with an A. Then we go S1 to S0 with a B. Then we go S0 to S0 with the same B. And excuse me. And our word is finished. It has not reached the accept state, and hence ABB is rejected. Lastly, AB. So A like this, B like this, A like this, B like this. The entire word is over and still hasn't reached the accept state, so this word is also rejected. Lastly, our example AAB will be accepted because it goes A once like this, then it goes A the second time like this, and it reaches the accept state. Okay? Is it sort of clear what an automata is doing?
No, AAB is not state.
Hello?
AAB is not a actual state here.
AB, what do you mean it's not an actual state? I've set S2 as my accept state. So when I go AA twice like this, I reach the accept
It's not
state.
become a language here. AAB.
I'm sorry?
Where should B go?
Where should B go? No, it is enough for it to see that AA is resay. It is enough for it to reach the accept state, to accept the word. So B is not even read. It is accepted before it reads B. So if I had AAB, or if I had AAB, AB, anything after that, they're all accepted just the same.
But it shows like you are starting with the AB, but ending with only B, A, only A.
Oh, you want to see... Wait. So you want something... here you go. Okay. You want something like AB, AB that ends with A like this?
Yeah. Only ending with A. Final state would be S2 here. How would you say B is the final transition?
I don't understand the question. So, how is B the final?
Okay. Here, I asked.
Hello? Hello?
Hello.
Yeah, go ahead.
Yeah. Here the automation you shown here, starting with A or B. The S0 is starting with A or B. With any middle of the transition AB, like that combination.
Mm-hmm.
But ending with only A.
Like this. Like this
Shown
example?
here.
Hello?
For example,
Yeah, go ahead.
AAA or BAA. But you show your string is AAB, ending with B.
So you're saying how come this is accepted while this being accepted makes sense?
It should be
You're
rejected.
asking how does it make sense to accept this?
Yeah.
So the reason is because for a string to be accepted, it needs to just, while reading, it just needs to reach the accept state. So the word, like, it only matters that it reaches the accept state at all. That's why, if, for example, in the previous examples when we were considering this as an accept state, us simply going like this was enough. We didn't need to continue on for, like, in this example, for example, when we took this word and we considered this as our accept state, we just went once like this, right? And it was accepted. Is that making sense? So,
in this transition, it's not showing any sense. The string with the ending with B, finest alphabet should be A. How should be B? My question is.
So, let me just redraw this, okay? So that I don't get confused about your doubt. Okay. So, as I raise this, just tell me which examples you want me to test and tell me which words being accepted / rejected don't make sense, okay? So I'll draw it now. Just give me whichever examples you want, whichever words you want to test now. And I will test those and I'll explain those. So we have starting state. Okay. We have B. We have A. We have B. We have S1. We have A. We have S2. In this example, S2 is our accept state. And go ahead, now give me your words.
A, B, A, B, B.
A, B, B. Next.
Is accepted. Okay. A, B, B is accepted or rejected?
We're going to test that now, no? So I'm asking for you to give examples because, like, I'm not really able to understand what your doubt is. So I'm hoping that if you give me words and if I, like, just do it manually in front of you, maybe it'll make sense. Okay?
Okay. But there were examples. The string is there, no? A, B, A, B, B. Is accepted or rejected?
I have to do that. No, I have to, like, do it and show you. So before I start doing, I'll just take examples. So
okay.
You were asking, right? Like, okay, this makes sense for so and so word to be computed. How is this word being computed? How is this word being accepted? How does that make sense and all that? So this is where I want you to give me the words that don't make sense. And we're going to do it. And we're going to see if they make sense at all for being accepted or rejected. Okay?
Okay.
So tell me 2-3 words, Akash.
Consider the example A.
A.
Yeah, 3 A's.
Okay. Any more examples?
Then consider the example B.
B.
Yeah. A.
Next.
Yeah.
Nishita, any more examples?
That's it.
Okay, I'll make 2 up. A, B, B, A and A, B. Okay, cool. And now we'll start computing all of them, okay? Okay, this will take more time than actually computing it. Right, there we go, finally. Okay. So, no, not finally. Okay, this thing is actually going to kill me someday. Please, just, yes, thank you. Okay, awesome. Okay, so we're starting from here. First we're reading A, so we go like this. Then we're reading B, we go down. We're reading A again, we go up. We're reading B twice. We're here, right? So we read like this and we go like this. And so this is rejected because it does not reach the accept state. So let me just write it again. So accept if word reaches accept state. Reject if word is read without reaching accept state. Okay, good. Oh god. Ugh, this thing is a nightmare. Right, there we go. Okay. Not much of a nightmare anyway. So next one, A. So A and then A, and it is accepted, and it doesn't need to read the last one because it's already been accepted. So this is, I think, where you would have a doubt. So does this make sense, Akash? I've reached my accept state, and so it doesn't matter what the next digit will be or the next character will be. Once I've reached the accept state, once the word has reached the accept state, it is accepted. If the word is completely read...
It makes sense, Farhan. Like, are you not ignoring the rest of the sequence that is followed by the first two patterns?
Well, DFA is pretty dumb, yeah. DFAs are pretty stupid. They're not directly applicable on their own. But this is a very important basic model to start with. This I'm introducing to understand acceptance and rejection. So if you're wondering about how we can even use DFAs, don't wonder, because there's not much you can do with them, or at least not much practically. They can be very interesting, can make many interesting like DFAs that do interesting things, but they're overcomplicated or they're just convoluted, and so they are pretty stupid because they're not really great at detecting languages. So I guess that's why a lot of y'all weren't really, were mostly confused, because it seems pretty useless on its own, right? And that's the truth. It is. It is quite useless on its own. And so I am just building some sort of like comfort with Automata for now, okay?
Okay.
So with the whole exposition done, does the concept of acceptance and rejection make sense? Now with this new lens that we don't really care that much about the rest of the word as long as it reaches the accept state. You can look at it in this way. This automata over here, where's my pen? Okay. This automata here, if I want to answer the question of, where do I write this? What words does this accept? Then the answer is words with a double A in them, anywhere in them, that's why I say just vaguely in them. That just means that anywhere inside the string, if I have a double A like here, or here, or here, then my word is accepted. Whereas if I don't have a double A, then they're rejected. So you saw over here, there is no double A over here. Similarly, if I do this, and do this, and do this, you will see, not the last one, just, where's my pen again? Yeah, this one, and this one. You'll see that they're rejected. So I will go ahead and do them right now to show, okay?
But in case you should, the string is infinite A's means it should be accepted or rejected.
So that goes back to our original definition. You remember how we said that our words are finite sequences constructed from the letters?
Okay. Oh, okay.
Right? So we're not considering infinite sequences right now. Okay?
But in accepted state, if we draw a loop to the S2 state, A means it should be accepted, A. But here the not make sense.
Which example, Akash?
A.
A is accepted, no?
So many number of A's will be accepted at the end. It's a finite state also. In case 10 A's, it will be accepted.
Yeah, it will be accepted. Because if I have 10 A's, then clearly I have somewhere where I have 2 A's next to each other. So they're accepted.
In that case, we need to draw a loop for the transition diagram.
No,
Why
we don't.
do we simply say...
So the first 2 A's that I take, if I have like A, then the first 2 A's that I take, that is enough for me to go over here. If I just read these two, and as I said, the word is accepted as long as it reaches its accept state, right? So the moment it reaches its accept state, I don't care about the rest of what happens over here. It's already accepted, so it's fine. And that still is in line with my answer over here, that it accepts words with a double A in them.
Yeah, okay.
Now I'll just take a very simple example like B, A. You'll see that this is also accepted because the first time it goes B like this, and then it goes A, and so it's accepted. What about A, B, A, like that? So A, B, A. So this is also accepted. Okay? So I've constructed this automata with this sort of idea in mind, that I want my automata to accept words that start with, accept words that contain 2 A's like that. Okay? So this is why maybe it seemed a little confusing, because this seemed to come out of like nowhere. But if it makes any sense, I constructed this automata with this in mind. So this is the reason why it acts like this, okay? So not all automatas are just going to randomly behave some sort of mysterious way where, it decides that it wants words with the A, B, A in the middle. No, you have to construct them specifically for that. Okay? Now,
if you consider the DNA sequence in a general form, to get a specific type of sequence.
Tell me.
In that, we do this non-deterministic finite automata.
Non-deterministic.
We can't get correct sequence what we accepted.
What do you mean get the correct sequence set? So you're giving a sequence into your NFA, and you're asking if it's accepted or rejected.
Find out in the whatever we accepted sequence.
Matlab? I don't understand.
In this case, plain scenario, in a general way, if you want to fetch the what we want that sequence only, like starting with A, B and ending with B, only B. Single
So,
B.
okay, so you're asking me how can I make such an automata?
Yeah. It's not deterministic. It is a deterministic finite automata.
Yeah, exactly. You don't need non-deterministic at all. Okay, cool, easy. So, well, okay. What did you want? You wanted it to start with A, B or something?
Okay.
Okay, wait, how about this?
I understand.
Okay, cool.
How do we relate this automaton with the DNA sequence?
Basically, like I told you, we treat our alphabet with as though it is A, C, T, G. And the question now becomes of what is my language that I have to solve, or in some sense. Now, this is sort of the direction, or like, in like a hand wavy way. However, the way we're implementing this is by something called third automata. And a third automata is something I sort of made up to study irrational numbers. And they were useful. Say I had a really long numerical sequence like 1 to 1.2. Excuse me. 1.2187955167 and so on, something. Okay. So my task was to say or is it possible for this number to be rational. Okay. And basically I'm given a finite amount of digits that come from some calculation, and I have to determine is this rational or irrational. And what it means for something to be rational or irrational in this sense is that let's take just 1 by 3. So if I decimal expand, this is just 0.33333. I can just write this as 0.3 repeating. Similarly, what's some other one? I can write a rational number like 0.232323 like this. 0.23 repeating. And so, a rational number oh god, okay. Wow, Lord, chill. Okay. Where is this thing? Yeah. A rational number has the following property of our interest, that is, it contains a repeating subsequence. So if you take numbers like root 2 or pi or e, cube root of 3, any irrational number you can come up with, they do not have repeating subsequences. So in some sense, you ask a question about why is this even related to genetic sequencing, right? You see a lot of the time repeating sequences in your genetic sequence. So in some sense, this thing is kinda rational. And this intuition between whether something is rational or irrational comes from the study of the sequence, right? And basically its subsequences. And so this is my motivation about why we should look at the way we're studying rational numbers and irrational numbers, and why we should try to relate the same tools to our genetic sequencing. Okay. Does this make sense? Is this well motivated enough for everyone? Does anyone still fail to see the point? Alright, cool. 2 thumbs up. All the support I need. Okay, so with that in mind, will I have time to talk about... Okay, I do not have time to talk about that automata today. Let's see. I will just put... Nah, I'll just keep this for the next session. I cannot finish third automata in one thing. Because for me to do that, I have to explain where, like, how to first calculate it on its own. Then I have to talk about why it's an automata. And then I have to draw its state diagram. Now, third automata, basically, for our toy example, third in base 2 is we're going to use, you and me, all three of us, we're going to use this to understand how thards work. Third base 3, okay, this is for understanding thards. The next one we're going to be using understanding state diagrams for thards. However, third in base 4 is a real monster. Terrifying. This thing has what, 20 or is it 45? I think it's 45 different nodes. Terrifying beast. And so, yeah, this is going to be our main tool. Moreover, we're going to try to implement concepts. So taking our third base 4, we're going to try to implement stuff from probabilistic automata. And while I'm like just chucking really long words at you, I may as well tell you the final goal of this thing. So our final goal is to, chuck in our sequence with, A, C, G, T, A, C. We're supposed to just chuck it over here. And what we expect is we want something called an equilibrium distribution, which is, as while I'm on the path of just chucking words at you, it is the eigen value or distribution. It's the eigen distribution over the stochastic graph. A graph, I'm saying, matrix of our, I put quote because it's technically not a Markov chain, but a Markov chain. So, because I don't have anything else left to do, I may as well give you a big picture. So this is where this project is heading. I don't expect it to take too long because the only thing that I personally don't know how to do is get this data. And another thing I don't know how to do personally is to, first of all, code this and implement stuff from probabilistic automata. So the coding part, either I will learn or I will ask someone to do it. And once that is done, we'll figure out where to get our data from. And once that's done, we will, we will probably read papers on probabilistic automata. I encourage you all to please bring any sort of information about genomes, because I'm assuming you guys are probably from a bio background, right? Both of you are?
Yeah.
Okay, cool. I'm from a math background. So to me, these are just alphabets. And so I'm going to treat them like that. So what you're going to be useful for is you're going to be able to tell me about structures within, say, alphabets. So if you tell me, oh yeah, AC and AC are more likely to link than TG and TC or something, then that is useful info. Okay? Maybe another thing we can find is some sort of information. Maybe we can figure out some sort of information like, oh, these two groups are more likely to, form so-and-so subsequence. Anyways, those kind of information. So all the interesting things that we can say, where's my pen again? There's it there. Okay. All the interesting things we can say will come from our equilibrium distribution. Okay. So next week's session, I'm going to talk about the third automata, and it is going to be entirely from a math-ish point of view. So you're going to see things that just look like number theory over and over again. And when I've explained third base 4, that's when, so until third base 4, I encourage you to at least keep an interest, because I know, okay, yeah. Excuse me. So I know it can seem boring to see numbers right out the gate, and so I really want you to think of these numbers as your characters in disguise, like your ATCG in disguise. So just assign 1, 2, 3 as maybe TCG, exclude A if you don't like A, and just have that as your mental picture, and that should be enough to at least allow you to survive the next class. And with that, after we've explained third base 4, this entire thing is going to be very collaborative. We're all going to be giving our inputs. We're all going to try to either find this. We're going to first work towards finding this equilibrium distribution, and then it's going to be even more collaborative. We're going to just say, oh, I find this subsequence interesting. I'm going to conduct a study on it. Stuff like that. So literally the next session is the only time you're going to have to just listen, because next session onwards we can all have proper discussions instead of this being a classroom or something. Cool. I will see you guys next week then. Is any doubts? Do you have any doubts? Yeah, go ahead, Akash.
For this genome, what should be free knowledge we want to gain for this research?
From a bio side, I have zero clue. I do not know anything myself for the bio part, because to me, I'm treating this almost like irrational numbers in base 4. So all the knowledge I'm aware of is strictly from math. So hence that's the point of view that we're treating this project from. But when it comes to this equilibrium distribution thing and this Markov chain and everything, that I'll explain when we're done with third base 4. Max to max, this will take one session, or I'll just send a video that explains this well enough, so that in the third session we can actually sit and collaborate. But as far as I know, I don't think, not as far as I know. Yeah, there is no prerequisites. And another thing is we're hopefully going to just give these results to that professor who came at Rocks from ISC. So once we've found this distribution, we're just going to send it to him. Hopefully it's useful to him. Did that answer your question, Akash? Yeah? Okay, cool. Okay, so you guys still interested in continuing?
Yes.
Alright, awesome. Then I will end today. I will put this up maybe in the next 2 days, depending on how free I am. And yeah, if you want to revise anything and stuff. Cool. Chalo, everyone take care. Have your dinner and stuff. Bye bye.
Wait.
Yeah, go on. Tell me, Akash.
Wait, 1 minute. How is this meeting will going on soon?
How is this meeting? What?
In the upcoming days, how the meeting will be going on? You want to continue or any related professor will come to these?
So I will be continuing. Until we get our equilibrium distribution, I'll be continuing. And then once we have any interesting results, we email these results to professors, or we write these results in LaTeX as formal, like a formal research paper. And then we can mail that research paper to professors. So almost any action we take later on completely depends on our results. So we can't even talk about anything until we finish getting our equilibrium distribution.
Thank you.
Alright. Take care. Good night.